Section 2.6, Domain and Range. Two terms we hear quite often when talking about a function is the function's domain and the function's range. The domain of a function is the set of all permissible values for the input variable. These are the values that we're allowed to plug into the function. The range is the set of function values that correspond to the domain. So the range would be the set of all possible values of the output variable. Now we're going to find the domain and range of each of the following functions that are defined by graphs. When finding the domain, visualize how we could compress our graph onto the x-axis, almost as if we decided to take the graph from top to bottom and smash it so that way it is lying flat on the x-axis. Well, the first point the graph would touch would be here at -2. And if I compress this point here, it would compress here at x equals 1. Now the rest of the line would compress everywhere in between -2 and +1. Now remember, the domain is all the possible values we can input into our function, which would be represented by our x values. So we can see our domain would be all the values from -2 to 1, which we can write in interval notation. Since -2 is in our domain, as indicated by the solid dot, we will put a bracket. Since 1 is also part of our domain, indicated by the solid dot, we would also put a bracket. Next, for the range, we're going to think about how the graph would compress onto the y-axis if I start from the left and right and squish the graph onto the y-axis. Here at the point -2, 0, I can compress it onto the y-axis there. Same thing at the 1, 3, I would compress it there. Every other part of our graph would compress in between y equals 0 and y equals 3. Our range would be the interval from 0 to 3. We would put a closed bracket around 0 because of the closed dot, and a closed bracket around 3 also because of the closed dot. So the domain of our function is -2 to 1, including -2 and 1, and our range is 0 to 3, including 0 to 3. Next, we're going to find the domain and range of our second graph. Starting off with the domain, notice how we have this open dot here at -3, where if we compress down to the x-axis, we put an open dot there at x equals -3, and we have this closed dot ending our graph on the far right, which if we drop it down, would go to 2 on the x-axis. And every other part of our line, if we were to compress it down to the x-axis, we see would shade everything between -3 and +2. So our domain would be the interval -3 to 2. Now, because -3 has an open dot above it, we'll put a parenthesis, and because 2 has a closed dot, we'll put a square brace. Now, as for the range, if we compress the open dot onto the y-axis, we would put an open dot because it's not part of the graph, but it's pretty close to it. And the closed dot on the right, when we compress it to the y-axis, you'd wind up at 2. And our graph does shade everywhere else in between. So our range is the interval 1 to 2. 1 is not a y value for any point in the graph because the only point that has a y value of 1 is an open circle. So we're going to put a parenthesis around 1. 2, we're going to put a square brace because we do have that closed dot that has a y value of 2. So our domain is the interval -3 to 2, including 2, excluding -3. Our range is 1 to 2, excluding 1, including 2. Now to find the domain of our next graph, at the far left, we have this closed dot, where if we compress, you'd have a closed dot here at -2. At the far right, we have an open dot, which when we compress down to the x-axis would be an open dot. And if we drop every point in between on the graph down to the x-axis, you see it would shade everywhere between -2 and +1. So our domain would be the interval -2 to 1, square brace around -2 due to the closed dot, parenthesis around 1 due to the open dot. Now we do have to be very careful when we find the range. If I start at the top left of the graph, I do compress it to a closed dot on the y-axis, and same thing with the open circle. I can bring that over to the y-axis as a 2, and we can tell that everything in between is shaded by the left branch. But we do have to be careful. There is this point here that does also have a y value of 2 on the left-hand side of this graph. Well, if I compress that over to the y-axis, that's going to fill that open circle. And I still have everything else in between all the way down to where y equals 1. So despite the open dot, there is a point on the graph on the opposite side of it that does have a y value of 2. So our range, we can see after we compress the graph onto the y-axis, the smallest possible y value my function can be is 1, and we're going to close it because we do have the point at the very bottom with a y value of 1, and our highest y value is 5 due to the top left endpoint. Despite the closed dot on the point 1, 2, we do include 2 in our range because we also have the point -1, 2, which is part of the graph. So 2 is part of the range. So our domain is -2 to 1, including -2, excluding 1. Our range is 1 to 5, including 1 and 5. Now we're going to find the domain of our next graph. Well, the right endpoint is already on our x-axis, but notice here we have the arrow pointing to the left. That means our graph is going to continue going leftwards forever. When I bring points down to the x-axis, everything to the left of +4 is going to be shaded by some sort of point when I drop it down to the x-axis. As for my domain, everything in the far left is in my domain, so I'll put a -infinity. Remember, -infinity always gets parentheses. And my highest x value is 4. Since I do have the closed endpoint at 4, 0, I will include 4 in my domain. Next, for the range, if I take my point 4, 0, bring it to the y-axis, I can see my lowest point is 0. But again, going to my arrow, it is pointing slightly upward. So even though it's going to be a slope road, it is going to rise the farther left I go. So my range is going to be from 0, close bracket around the 0 because it's the point 4, 0, to infinity because the graph is rising forever. The last graph we're going to look at is a little bit more interesting than the others because you can see it's broken up into segments, specifically 3 segments here. To find the domain, we'll focus one segment at a time. If we take a look at our first segment, projecting it down to the x-axis, we would have a closed dot at 1, open dot at 2, and everything else in the middle would be overlapped by some point on that segment. Now we can move on to the second segment, and similar to the last segment, we have a closed dot on the left, open dot on the right. Well, if we bring the closed dot down, it's going to overlap with the open dot, so we're going to fill it in. As for the 0.32, we'll bring it down to an open dot on the x-axis and shade everything in the middle. And then in the last segment, similar to the other two, we have a closed dot on the left, open dot on the right. If we project the closed dot down, it does overlap with the open dot from the previous segment, so we'll fill in the open dot, bring down the 0.43 onto the x-axis as an open circle, and everything else in the middle will be filled in. So from what we see, everything between 1 and 4 is shaded, but 1 itself is part of the domain because we do have the solid 0.11. However, the 0.43 is not part of the graph, nor are there any points on the graph with an x component of 4, so 4 gets a parenthesis. Now, the range of this graph is very interesting. If I take any point on the first segment here, they all have a y component of 1. So that entire segment is going to compress onto 1 on the y-axis. Similar to the first segment, the second segment has a y value of 2 for all of its points. So if I compress the second segment onto the y-axis, I would just have all those points there at y equals 2. And the same thing goes for the third segment. All the y values are 3. So when I compress the line segment onto y equals 3, they would all compress to that 1 point. So all my possible y values for this graph are 1, 2, and 3. Instead of using interval notation, we're going to list it out as a set using the curly braces. And my range is the set containing 1, 2, and 3. I cannot put the interval 1 to 3 here, even though, yes, 2 is in between 1 and 3, but consider a number like 1.1. 1.1 is in the interval 1 to 3. However, 1.1 is not a y value that we can obtain from any point on the graph. So saying that the range is the interval 1, 3 would be incorrect. Now we're going to find the domain and the range of the following functions that are defined by equations. Now, it's fairly easy to find the domain of a function based off of its equation. It's based off of what are we allowed to do or what are we not allowed to do with the operations we see. If I take a look at f of x, that equals 1 over 2x minus 3. The 3 operations I see that I would have to perform are multiplication and then subtraction. Well, I can take any 2 numbers and multiply with no problem. I can take any 2 numbers and subtract. That's not a problem. However, division, our last operation, can be a bit problematic. The one number we're not allowed to divide by is 0. So if 2x minus 3 was 0, our function would be undefined. So we want 2x minus 3 to not be 0. Now, even though I'm setting 2x minus 3 not equal to 0, I'm still going to solve as if it was equal to 0. And I get x cannot equal 3 halves. So I can plug any number I want into my function for x except for 3 halves. If I were to write this as an interval, well, I can plug any number smaller than 3 halves in. That'll be the interval negative infinity to 3 halves, or, which I'll use the union sign for, I can plug in any number bigger than 3 halves, which is 3 halves to infinity. And there's the domain of f of x, negative infinity to 3 halves, union 3 halves to infinity. The range can be a little bit harder to find by looking at the equation. Usually we would have to rely very heavily on properties of our operations to try to help us figure it out. So we're going to take our function and we're going to plug it into Desmos to help double check our domain and to check our range. So we're going to take our function and plug it into Desmos to help us double check our domain and also find our range. I can see the graph of our function here in blue. Now notice how for the domain, which is all the possible x values, 3 halves would be located right where my mouse currently is. And if I go up or down, you can see that the blue graph gets very, very, very close to this vertical line marking x equals 3 halves. However, my blue line never crosses. And if I go far right and I go farther left, you can see that I continue to go right and left away from the 3 halves forever. And we do get the shape of the 1 over x function that we've seen in previous examples. And you see that we get the shape of the 1 over x graph, the reciprocal function that we saw a few sections ago. So this does double check our domain that x cannot be 3 halves. Now, what about the range? Well, if I keep scrolling my graph down, you can see that I do tend to go down forever. But what's interesting is at 0. Notice how at y equals 0, my graph never actually crosses as I move left. And if you trace along, notice how all the y components are negative, but getting closer and closer to 0. Same thing goes if I go to the right. If I trace the points on the right, notice how I'm getting closer and closer to 0, but my y values are staying positive. This tells me my graph cannot cross the x-axis, which means my function can never equal 0. So for the range, well, I can get negative answers because we can see that from the sharp drop downwards. So we'll have the interval negative infinity to 0. Union, well, y cannot be 0, so we can't include 0. But we did see, if we trace back, that our graph does sharply rise. So my function could be any positive number, which would be 0 to infinity. And there's my domain and range. Now we'll find the domain and range of g of x, which equals negative 3 minus the square root of 2x minus 3. Now, taking a look at the operations and seeing what we're allowed to do or not allowed to do, well, here we're taking the square root. We can't take the square root of negative numbers and get real numbers out of it. So if I take a look at the 2x minus 3, in order for the square root operation to work, I need the 2x minus 3 to either be positive or 0. So I'm going to set the 2x minus 3 greater than or equal to 0. And now we solve our inequality. And when we solve the inequality, we get that x is greater than or equal to 3 halves. So our domain would be the interval 3/2 to infinity. We have a square bracket around 3/2 because we can plug 3/2 into our function and we will get a real number out of our function. Now let's take our function and plug it into Desmos. And here we have the graph of the -3 minus the square root of 2x minus 3 here in blue. First, let's double check the domain. Notice how our g of x is making the same shape as the square root function, just upside down. And you can see that the graph of our function has this hard stopping point here at the point 1.5, -3. And keep in mind, 1.5 is the same as 3/2. So the lowest x value we can plug in is 3/2, which is precisely what my inequality and my interval is indicating. And I can plug in any x value bigger than 3/2. And you can see as we zoom out, the graph does continue to go farther and farther left. So we can plug in any number bigger than 3/2 we want. Our domain was correct. Now, what about the range? Well, because we know this is a square root graph, it starts at its starting point, and it just goes forever in one direction. Now, here we can see it goes down towards the right. So this starting point is going to be the highest point for this graph. So for our range, our highest value is -3. And we're going to put a square bracket around the -3 because we know it's the highest value. Now, is there a lowest value for this function? Well, no, because if you continue to trace right, you can see that it keeps going down forever and ever. Granted, this descent is very slow, but it does drop forever. So our range would be all numbers less than or equal to -3, which we would represent with the interval -infinity to -3. In our last few examples, when we were finding the domain and range, we didn't assume the independent and dependent variable had any real-world representation. However, when we are working with application problems, our variables do have real-world meanings, and these real-world meanings come with restrictions. When we restrict the domain based on what is possible in the world, we call this the practical domain. In other words, when we're dealing with real-life problems, instead of using every single thing we can plug into the equation, we're just going to restrict our variables to what is actually possible. As an example, suppose h of t represents the height of the ball t minutes after being thrown. Since we can't go backwards in time, the smallest value for t would be 0. But what would be the largest t we could use? Well, once when the ball hits the ground, it stops moving. So the highest value of t is going to be whatever time the ball hits the ground, when the motion actually stops. So we're going to restrict t between 0 and the time it lands. Now, the range that corresponds to the practical domain, we call the practical range. Suppose you purchase 20 balloons for $5. You plan to make balloon animals at the fair and sell them for $1.50 each. Your profit can be determined with the function p of x equals 1.5x minus 5, where p is the profit and x is the number of balloons sold. First, we want to identify the practical domain of the function. Recall that x is the number of balloons sold. Well, does it make sense for x to be negative? Well, no. How do I sell a negative number of stuff? But I can sell nothing. So it is possible that the lowest value for x is 0. Now, what about the highest value of x? I'm told that I purchased 20 balloons. So I only have 20 balloons I can sell. Does it make sense for me to sell more than 20 balloons if I only have 20 balloons? No. So the highest value x can be is 20. So my domain is the interval 0 to 20 with closed brackets, since I can sell no balloons and I can sell 20 balloons. Now, how can we use our practical domain to find the practical range? If we go to Desmos, we can start off by typing in our function. Well, notice when I type in my function, I do get a line, but my line goes on forever in both directions. Well, just like with piecewise functions, we can restrict our function by using what we want to use for our practical domain. But we can restrict our function to the particular domain by typing in our condition for x. The interval 0 to 20 means that x is between 0 and 20, and x can be 0 and can be 20. So the interval 0 to 20 is the same as saying 0 is less than or equal to x, which is less than or equal to 20. Notice how when I put this at the end of my function, my graph is a line segment. It doesn't go on forever anymore. From here, I can see the endpoints of the line segment. The smallest profit I can make, which is going to be represented in the second component, is -5. Our highest possible value for p occurs up here, which would have a value of 25. So our highest possible value for p is 25. Since p of x can equal -5 and 25 on this practical domain, we're going to put closed brackets around the -5 and 25.